Okay, so today we're going to learn another shortcut, which is a derivative rule, which has to do with the chain rule. Now, the chain rule is specific to functions that are composite functions. And so at first sight, you might think certain functions you could find a derivative of without having any problems. For example, I'm going to put something up and see if you could find this derivative yourself. So the question is, how would we find the derivative of f of x equals to the square root of x squared plus 4x. So if you think about it, this is kind of like a function within a function. And so take a minute, see if you could find this derivative. You should pause this video and see if you could find it. And if you try to find this, you probably, what you did is before you found a derivative, you wrote this as x squared plus 4x to the power of 1/2. And then the question becomes, well, what do I do here? And the answer is, we right now do not have the skills to find this, because what happens here when you use the power rule, the problem before is when we use the power rule, like it was something simple like 8x to the 5th, we could use the power rule, which would give us 40x to the 4th. However, this is more than just that. So in fact, what you notice is this is a composition of functions, right? If you could think of it, the chain rule specifically applies to composite functions. So just keep in mind that that's how it kind of, we're going to treat this. So anytime you're asked to find a derivative of a composition of functions, you're going to use the chain rule. So I also talk myself through these derivatives just like any other derivatives, and I'll explain to you how that works the way it does. So let's talk about the chain rule. So what does the chain rule say? It says if f and g are both differentiable, and let's define capital F as that function f that is composed of f and g. So capital F is the composite function of f of g. This is the composite function defined by capital F of x, which equals to f of g of x. Then capital F is differentiable and f prime is given by the product. And here's what f prime is going to look like. And I'll kind of talk you through how the derivative of f prime is found. So f prime of x will equal to f prime of g of x times g prime of x. So basically, the way I think of it is, I think of this as like functions within functions. So what I do is, if I'm given a composite function, I basically say, okay, look, the way this works is we find the derivative of the outside. So we work our way from outside inside. So we would say the derivative of the outside, which notice how it's f prime of g of x, times, then you go in and you say the derivative of the inside, which is g prime of x. So if you notice, it's kind of like a multi-step process. And by the way, as long as we have composite functions, this is always true. So when this is a composition of 2 functions, but I could have a composition of 3 functions. So for example, we could make a comment here. Note, let's say if capital G of x is defined as f of g of h of x, See, if I said find the derivative of this, you'd notice, wait a minute, I have a composition of functions, so I have to use the chain rule. So it's kind of like you're working your way from the outside all the way in. So g prime of x would be what? The derivative of the outside, so the furthest out is f prime of g of h of x. Notice how I'm not finding the derivative of g and h. I'm just going one at a time. So you first find the derivative of f. Then you say times, then you go inside. So once I took care of f, I go inside. The next function is g. Then you say g prime of h of x. Then you say times, and finally you keep going in until you can't go in anymore. The derivative of h, which would be h prime of x. And so that's basically what the chain rule looks like. It's kind of like, I always think of the movie Inception. It's like a dream within a dream within a dream. I think of this as like a derivative within a derivative within a derivative. It's kind of like we keep working our way from outside all the way in. Okay, so the one other comment I want to make is the chain rule in Leibnitz notation, which is also important. We'll use this quite a bit. In Leibnitz notation, here's how the chain rule looks. So this is basically, Leibniz notation is just a different way of expressing the same thing that we just talked about. So this isn't anything different. So when you look at this, it may look different, but we're basically re-expressing the same thing in just a different format. So we're saying if y equals to f of u and u equals to g of x are both differentiable, functions, then here's what we could say. dy dx, which is, what are we saying? The derivative of y with respect to x. Which, do you see how this is pretty much a composite function? Because look at what we have here. We have y equals to f of u. So right now, y is in terms of u. However, u is in terms of x, because if I take u, notice how we have y is equal to f of u, but if I substitute in place of u g of x, which u is the same thing as g of x, then I'll be finding the derivative of this guy with respect to x. So notice, sure enough, this is a composite function because I have f of u, but u is g of x. So it's kind of like I have f of g of x. Okay, I hope that makes sense. If it doesn't, make sure to ask me in class and I'll be more than happy to clarify this. So what happens here? To get dy dx, what do I need to do? Since I'm working myself outside in, what do I get through? First, I have to get through y, and then I'll get through u. So what I need to do is first I find a derivative of y, which would be what? Dy du, which, what am I doing here? I'm finding the derivative of y with respect to u, times, then I have to find a derivative of u. And when I find a derivative of u, u is in terms of x, which would be times du dx. So in fact, if you think about it, this is in fact the chain rule, because I'm saying the derivative of this one, which is the outside function, times the derivative of that one, which is the inside function, which, sure enough, look at what happens to the du's here. They cancel out, and I'm left with dy dx. Okay, so this is just Leibniz notation for the chain rule. And when we get to section 10 of this chapter, which is related rates, that's when the fun stuff begins. And we'll use a lot of Leibniz notation. So you might not use it as much in this section, but Leibniz notation is going to be very important when we get to related rates, which is actually where all the fun stuff is anyway. So, you know, you should be looking forward to some fun stuff coming up within a few sections. So now let's go back to the first question I asked. So if you remember, for example 1, let's actually do this. We would say, find the derivative of f of x equals to the square root of x squared plus 4x, which, if you look at this, now we know how to find the derivative of this, because if you identify this, notice how f is a composition of functions. My outer function is the square root function. My inner function is the x squared plus 4x. So before I find this derivative, I'm going to rewrite this as x squared plus 4x to the power of 1/2. So now we begin. To find the derivative of this, I start with the outside, which if you look at the outside, what do I have? I have the square root function, which means how do you find the derivative of the square root function? You use the power rule. And I'll make a comment on the power rule because, see, we're literally, what are we doing? We're combining the power rule here with the chain rule. So, in fact, that's what the chain rule is all about. So then, what would f prime of x be? You first worry about the outside. So the outside function is the power of 1/2. So you bring the 1/2 out front. Notice how I'm not going to touch anything with the inside. The inside stays the way it is. So it's the derivative of the outside, which is 1/2 times x squared plus 4x to the power of negative 1/2. Okay, notice how I took the derivative of the outside. Now, once I do that, now I'm ready to go inside. So then I would say times the derivative of the inside, which is 2x plus 4. And notice how once I get through this, I have nowhere, I can't go in any further. So this is actually my derivative, which I use the chain rule. Okay, so let's do a couple more examples. So for example 2, we're going to say, and you should probably try to do this on your own. Okay, we could say differentiate y equals to 3x squared plus 5 to the power of 20. So pause the video, try to find its derivative on your own, and then play it again and verify your answer with mine. So continuing on with this, what we notice is we have a composite function once again. Okay, so since this is a composite function, I would say, okay, the outside function is the something to the power of 20. So we start off with saying, okay, y prime would be the derivative of the outside, which means to find the derivative of the outside, I would have to use the power rule. So bring the 20 out front. So it'll be 20 times 3x squared plus 5 to the power of 19. Once again, let me point out, notice how I haven't found the derivative of the 3x squared plus 5. You see how this, once I find the derivative of the outside, what's on the inside doesn't change. It stays the way it is. And the reason why I'm being so specific on this is one common mistake people make is we kind of move too quickly, or they rush the whole process. They find the derivative of the outside and the inside at the same time. And I'll show you what I mean in a minute. But we just found a derivative of the outside, which is this guy. So now I could work my way inside, which is the 3x squared plus 5. So it'll be times the derivative of 3x squared plus 5, which is just simply 6x. Okay, so just to kind of go back to this, a common mistake people make is they say the derivative of this, and this is incorrect, by the way. So if you're listening to this, remember what I'm going to do right now is completely false. Some people do this, which is a common mistake. They say, okay, the derivative of the outside, which is 20 times, and this will be a 19 times, and they find the derivative of the inside and they put it here like this. So you see what I did, the mistake I made is not only did I find a derivative of the outside, I also found a derivative of the inside at the same time, which this clearly looks nothing like that. So this is false. Okay, so moving on. Example 3. Let's have you try this out. So differentiate y equals to 2x divided by 3x squared plus 1 all to the power of 5. So once again, pause the video, try to do this on your own, and then once you're done, press play again. So looking at this, to find the derivative of this, once again, notice how I have a lot going on here. So I could already see that this is a composite function because I have something to the power of 5, and then the inside function is a rational function. And so for a rational function, I'm going to use the quotient rule. So remember, when you're finding these derivatives, you could use multiple rules as long as they're appropriate. So I'm going to use the chain rule, but when I work my way inside to find the derivative of the inside, I'm going to have to use the quotient rule. So this would be y prime equals to the derivative of the outside, which bring the 5 down. It'll be 5 times 2x over 3x squared plus 1 to the power of 4 times the derivative of the inside. Now to find the derivative of the inside, I have to use the quotient rule. So what does the quotient rule say? The derivative of the top, which is 2, times the bottom, minus the derivative of the bottom, which is 6x, times the top all over the bottom squared. And there's my derivative. So at this point, if you want, you could simplify a little bit, but remember, we don't necessarily need to simplify, but you could if you want. And I think as far as I would go is I would just simplify this part here and maybe combine some stuff to kind of get this as a single expression, but I'll leave that up to you, okay? So moving on to example 4. So for example 4, we have y equals to e to the power of sine x. So if you look at this one is not as straightforward as the other ones that we've done. But if you look at it once again, it's a composition of two functions. See, what's the outer function? Well, if you look at this, the first function you'd run into is what? E to the sine x. That's how we would do this. And then once you find the derivative of that, then you work your way in. And as I go in, I'm going to go into sine of x. Okay, so it's kind of like outside, inside. So to find the derivative of this, we say, what's the derivative of e to the sine x? Remember, the derivative of e to the x is e to the x. So which means the derivative of the outside will be just e to the sine x, which the sine x doesn't change because it just tags along, right? And it'll be times the derivative of the inside. And what's the derivative of sine of x? Well, that is cosine of x. So there you have it. The derivative of e to the sine x is e to the sine x times cosine x. Okay, so I hope you see this process, and you know, it's just not that difficult. All we do is we start from the outside and then we work our way inside. Now remember, the inside function, once you identify that when I find the derivative of the outside, this inside function isn't affected until I work my way in. So notice how the sine x didn't change. But then where did this cosine come from? Well, that's because we're saying times the derivative of the inside. Okay, so the last thing I want to talk about, which if you remember a couple sections ago, we defined the derivative of an exponential. Okay, in fact, we know that the derivative with respect to x of e to the x, the derivative of e to the x is just going to be e to the x. Okay, and that's a nice result. Now the question is, well, what's the derivative of a to the x, where my base is no longer e, it's just any other base? And that is actually going to be very, very similar. And in fact, this next derivative that I give you of exponentials, I'm going to point out to you that e to the x also follows this rule, but there's something that we don't bother writing because it'll be a waste of our time. So let's take a look at this. The derivative of exponentials is defined as following. The derivative with respect to x of a to the power of x. Notice how this is an exponential function, except my base is no longer e. So this is the same thing as a to the x, which notice how it's following this rule. The derivative of e to the x is e to the x. So the derivative of a to the x is also a to the x, but it also has times the natural log of a. Okay, this is an a. Okay, times the natural log of a. So the derivative of an exponential of base something other than e is very similar to the derivative of e to the x, except it has an extra ln of a. And here's the thing. I claim that this rule is also applied to this, except we don't bother writing the ln of a. And hopefully you guys could guess why, because look, if I went off to the side and said, look, the derivative of e to the x with respect to x, of e to the x, that's the same. If I'm using this rule, what would that be? You'd say that's the same thing as e to the x times ln of e. And if you notice, wait a minute, what is the natural log of e? The natural log of e is 1, so I actually get e to the x times 1, which is e to the x. So the reason why we didn't put the ln of e here, because it would have been a little redundant, because ln of e itself is 1. So this is the difference. So if you get an exponential that your base is something other than e, it'll just be a to the power of x times the natural log of whatever that base is. So we like working for e to the x because it's kind of like we lose this. It's not that we lose that ln, it just becomes a 1. So the derivative of e to the x is e to the x, and the derivative of a to the x is a to the x ln a. Okay, so that basically wraps up this section. I know the notes are fairly short, but it was just strictly all about the chain rule. So from this point on, we now have three rules of differentiation. One is the product rule, then we have the quotient rule, and now we have the chain rule. And of course, there's also the power rule and the trig derivatives and so on. But the three main rules that we've been using have been product, quotient, and chain.